Section 5.2, Part B, if you will. We're going to talk about a little bit more with integers, multiplication and division. And we had gotten through looking at some basic properties, many of which were repeated properties from before. All the ones we did last time were. And we're going to look at a few more facts this time to fill in for integers that come along with multiplication. So some theorems about multiplication for all integers. If you have negative a times b, then that's the same thing as having a negative, and then the a and the b multiplied. We kind of talked about that one when we were, both of these, when we were looking at our models and talking about the 4 times 3, we would already know it's the negative or positive that we were actually trying to confirm. If a and b are both negative, excuse me, then the negatives, quote unquote, cancel each other out. Has anybody seen the movie Stand and Deliver? Yeah? It's really old, so I don't know that necessarily you would have. What context did you see it in, Sam?
It was like a long time ago in 7th grade.
Okay. It's seeing it in a school environment. My methods students watch it every time I teach methods. It's actually about some. How about Freedom Riders? Have you seen that? Okay, it's a math version of Freedom Riders. Okay, they're both true stories. It's actually in, I think, Southern California. A lot of Hispanic kids, a lot of poverty and things like that. Anyway, the guy that's involved, his name is Jaime Escalante, and he drills into them a lot of these things, and so he says a negative times a negative equals a positive, and he has them repeat it over and over and over again. So that's what's going on this one, of course, is that a negative times a negative does equal a positive on 5.7 Part B. 5.8 actually shows what happens when we have subtraction in integers for the distributive property. It works just like if you have addition. There's no differences, so it's just what you would expect to have happen. No surprises. And then, what's left? Division is what's left. So let's take a look. When we're talking about division, just like when we talked about subtraction, we went back into subtraction is defined as being how addition is undone. This is the same idea here. So we learn division because we already know multiplication. And this looks just like what we did when we talked about whole number division. If you have a divided by b, it's going to be a unique integer c, if it exists, such that a is equal to b times c. And we'll do an example, and I'll use specifically a negative number, so I've got integers this time. 6 divided by negative 2 is what? It would be a negative 3, right? And the reason why, how you could help children to understand it, is because 6 is actually equal to negative 2 times negative 3. And that's what this statement here at the end is saying, is that it's the number that you need to multiply by negative 2 to get back to 6. Okay? Now, when we were in section or chapter 4, we talked about divisibility of numbers, and we said that a number, it divides another number if it doesn't give us a remainder. That was one of the ways we talked about it. We also thought of it as it goes in evenly, right? That was another phrase we talked about. And we always did it with whole numbers because we were still working before the introduction of integers in chapter 5. But divisibility works the same way for integers. A divided by b is a unique integer. Then it's divisible by b, or equivalently b divides a. And you'll remember, I hope, this notation, b divides a. Our next exam is 4 and 5, both chapters, okay? So that's part of that notation. So no remainders is the key. Inequalities, we talked about these with whole numbers as well. It's just that we didn't have the negative components to throw in the mix. For all integers, a and b, a is less than b, and it's written as you would expect from your previous exposure. If and only if there exists a positive integer k, such that a plus k is equal to b. And again, we could say, for instance, that negative 1 is less than 1. And it's because there is a number I can put in this blank that would make them equal. What number would that be? 2. 2. And you'll notice it actually says a positive integer right here. So if you were led to think, oh, maybe it's 0 or negative, that's not what we're looking for. So for instance, I couldn't say that negative 2 is less than negative 3, because the value that I would have to add to make this equal isn't a whole positive integer, right? It's not a positive integer. It would actually be negative. I could put a negative 1 in there and it would work, but it doesn't satisfy the definition. So this is not true. It's not less than. And then one more piece of information before, well, actually there's a couple more from before we get there, but it's on the same slide. Theorem 5.9 says that for integers a and b, a is less than b, or equivalently b is greater than a, if and only if b minus a is equal to a positive integer, i.e. b minus a is greater than 0. Again, we had this with whole numbers. It's not anything new. It's just telling you it works for integers too. So in other words, I'll use my same, what did I have? Negative 1 is less than 1 before. So the reason that negative 1 is less than 1 is because if I take the 1 and I subtract the negative 1, what is 1 minus negative 1? It's 2. And is that number greater than 0? Yes, and that will always happen. So even if we're dealing with negative numbers, that works. It works with two negative numbers as well. So let's say we had negative 3 less than negative 2. Well, it means I should be able to take the negative 2, the greater one, and subtract the lesser one. And what is negative 2 minus negative 3? That's 1, and it's still greater than 0, right? So that will always work when I'm testing these. Hang on, let me move that over here. And notice that. I'll teach you guys how to do some of this stuff when you come to my office for your presentation, okay? All right, our last theorem for the semester, until I see some of you again in August for some other class that we're going to do together, is Theorem 5.10, and it has the following in it. If x is less than y, then x plus n is less than y plus n. And we have seen that before with whole numbers. If you have two numbers and they have a less than relationship and you add something to both of them, they're still in a less than relationship. We talked about it, I think, I can't ever remember if I do this every time I do it or not, but I usually do, where if I'm shorter than you, aren't I, Michaela? Yeah, if I'm shorter than Michaela and we both put on 2-inch heels, I'm still shorter than Michaela, right? It's the same idea. All right, here's another one. If you have x less than y and you multiply it by a negative, then negative x is actually greater than negative y. And we could look at a couple of examples to talk about that in several different ways, but let me just do one that's pretty straightforward. 1 is less than 2, agreed? Yes. But if I put a negative on both of them, negative 1 is actually greater than negative 2. You can think about it from a number line if you like. That's a pretty good way to do it, right? If you're further to the right, you're a bigger number than if you are to the left. You can think about what would need to be added, right? This less than relationship that we talked about above on this slide over here, what would need to be added in order to actually make them equal, which one is less. You could also look at values that aren't necessarily both negative, right? So if I did negative 1 is less than 7, we would agree with that. And if we multiplied both of them by negative, here I get a 1 and here I get a negative 7, and it becomes really clear that the 1 is bigger than the negative 7 because they aren't both negative to be considering at the same time. So we can think about lots of those perspectives. Okay, still the same premise, x is less than y. Now I've got n as a positive number. So if n is a positive number and I multiply it, again, the relationship stays the same. That is that it's still less than. So if I talked about, we'll take mine and Michaela's heights again for an example. If I doubled my height, that is multiplied my height by 2, and I doubled Michaela's height, multiplied her height by 2, she'd still be taller than me because she was taller than me to begin with, right? The reverse happens if the number is negative. Notice that's what this difference is on part D here, if you will. The n value is negative. So in this case, the xn would then be greater than yn. And this is just a continued case of part B here. If I multiply by a negative, that would be the example. This example here would be the fourth example where n is -1, is what it really would be. And again, you could use examples. You could say, we'll take the one less than 4. We'll do that one. And let's multiply them both by n is equal to -2. So -2 times 1 would give me -2. -2 times 4 would give me -8. And which one's bigger? The -2 is bigger than the -8. So you can do concrete examples to show that. Any questions about those? Okay. The last little bit right here is just sort of it's not really a deviation, but it's also included in this section of material, so we're going to take a look. It asks us to find all integers that make the following true. It uses equations. It's actually equations, whereas most of the time we're not working with equations. However, simple equations are introduced at about end of 5th grade, beginning of 6th grade. I'm working with Dr. Marsh's proportional and statistical reasoning class. For those of you who've had that class, if you'll remember, we use hands-on equations in that class. They look like pawns and number cubes. Shake your head if you've had that class. You know what I'm talking about? Okay. If you haven't, that's fine. But those manipulatives are specifically geared at doing algebra at younger ages. Usually about 5th grade is where you see equations and x and stuff starting to show up, okay? So just beware, your certification for most of you puts you at that age level still. So let's take a look at how, as a remembrance of how we can solve these types of equations. Now on part A, there's more than one way you could start the problem. So I will let you tell me how to start it, and then I'll show you a second option after we do the first working all the way through. So what would you do if you were dealing with this particular equation and you need to figure out what x is? What'd you do, Emily? That's actually what I would do as well. So if I divide by -5, the beautiful thing there is that I actually eliminate this piece, right? I do, and I'm left with what's exactly in parentheses, x minus 3. What's on the right-hand side then? A 1, and then what? I would add 3. So what would my x value equal in this case? It would equal 4. And if we check it, it should work, right? So let's go back and check it, if not written down, at least sort of mentally. I'll write it down for us. But if I put in here a 4 minus 3, what's 4 minus 3? 1. And then what's 1 times the -5 at the beginning? -5. So it works, right? Okay, so for the rest of you, what other way did you think of to start the problem? To distribute. And that's perfectly valid as well. So if you distribute this, what will your next step look like? -5x, and then what? Good, you guys got the sign, good deal. Plus 15, because I have the -5 times the -3. And it will still equal the 5 on the right. Now what?
It's supposed to be -5.
Oh, I just copied it down wrong from originally. Thank you. Okay, much better. We would have gotten different answers. That would have been highly unfortunate. Okay, now what's next? Subtract the 15, right? Okay, so as we're working through the problem in this way, we have more steps. We have more of the adding and subtracting, multiplying going on, and we're going to divide here in a minute with the integers. Clearly, the whole purpose in doing that is that these two eliminate each other, right? But what do I get on the right-hand side? What's -5 plus -15? It's -20. Very good. And then on the left-hand side, I have my -5x. And what would I need to do? Divide by -5. So eventually you're going to divide by -5 one way or another. What would x be? 4. Same thing, yeah. -20 divided by -5 would be 4. Okay, so both perfectly good ways of doing the problem. Any questions on either of those? Okay. Now, on this problem, it looks kind of like there's some advanced mathematics going on in there because of those squareds. There really isn't. I'd like for you to remember a fact that you know, but you probably weren't thinking of it as soon as you saw this particular problem. If you were to take, I'm just going to use some random numbers, 5 minus 2 and 2 minus 5. What is 5 minus 2? 3. And what is 2 minus 5? Negative 3. How are they the same? Yeah, they're the same absolute value. It's the same numerical component, right? They have different signs, but the number part, taken just as a numeral, is the same. Everyone agree? And that works all the time. So on this equation, I have x minus 1 and 1 minus x. They're always the same. Do you understand that? They may have different signs, but the number part's always the same, no matter what x is. So, for instance, if I said x was 7, and I did 7 minus 1 and 1 minus 7, they're both some version of 6, right? One of them's positive, one of them's negative. And that's always going to happen. Now, what do you suppose then happens? I'll keep this here for the moment. When you square the value, they both become positive. They were already both 6s in my example. One was positive, one was negative. But once I square it, now they're both the same sign as well. Correct? So the reality is that I could put in any number in this equation and it works. Any number will work. Because when I square it, the sign gets lost anyway. So, for example, on this one, right, this would be 6 squared and negative 6 squared. And they both equal 36. There was absolutely nothing special about the number 7. Whoops, I meant to use an eraser. Oops, that's the one. You can pick something, well, I don't want to pick something too big. How about 10? And 10. 10 minus 1 would be 9, and 1 minus 10 would be negative 9. And when we square both of them, we get 81. And this would work if it's positives or negatives. Let me try a negative actually with you. What if I had a negative 2 here? That's a little bit more fun. What's negative 2 minus 1? What is it? It's negative 3. What's 1 minus negative 2? It's 3. And then again on both sides, I end up with a positive of the same value, in this case 9. So any value works on this particular one. Now, that's obviously a very unique situation, and it worked only because these two things matched, right? So you might look at this and say, okay, fine. So we've got a special case going on, but what if they didn't match? What if one said x minus 1 and the other one said 1 minus 2x, or something like that? What would I do then? So I'd like to show you another way to think about it that will work, and it will work for our problem, so I'm going to use it. But it's really kind of overkill for this particular problem. Are you with me? Okay, so this will work, but it's really not necessary in our case. Now, perhaps both of you, because you looked at both of these sides and you saw the square on both of these sides, what might you have thought to do to begin with, knowing the math that you know at this point in your life? To take the square root. You might have thought that. I want to get rid of a square. How do I get rid of a square? And square root might have been where you would have gone in that case. And square roots are lovely. They eliminate squares. But the catch is they also eliminate signs. So while this equation is true coming out of this, it is also true that we would get this equation coming out of this. And what I would like you to remember is a fact that you know about a very simple one. Let's go with x squared equals 9. If x squared equals 9, what could x equal? A 3 or a negative 3, right? Because the reality is that if I take a square root, somebody somewhere told you you have to put a plus or a minus on it. Do you remember that? Yeah, and you do. They weren't lying to you. They're correct. When you insert a square root into an equation, you, by accident, sort of, eliminate a sign. Okay? So we compensate for the elimination of the sign by putting a plus or a minus on it. And so what you see here is the plus part, and what you see here is the minus part of that same fact. What I've really done is put a plus or a minus along with the square root on one side. You just do it to one side. You only need it on one side. Okay? So if we try to solve these equations now, let's just do the first one right here that I've started. What might you do first or next as you continue to solve? Don't be shy. What might you do? You might add a 1. So you might look at this and say, okay, that gives me an x on the left and a 2 minus x on the right. What then? Add an x. So this gives me 2x on the left and 2 on the right. And then divide by 2. So what would x equal if I'm looking at the first case? 1. And that should make sense. If I plugged the number 1 into this version of it, I would get 0 on both sides, right? Because it'd say 1 minus 1 on both sides. So that makes sense. We agree x should equal 1. That makes sense. The second one's a little more interesting. On the second one, you might notice the negative on the right-hand side sort of screams, distribute me, right? So it's screaming at you. That's why your ears were hurting. What would you do next? Maybe you do the same thing you did before and add a 1. And if you do, what happens? Yeah, you get x equals x. And this is one of those cases where you feel uncomfortable because you're like, I don't know what to do now with x equals x. What does that mean? And if you try to keep going and sort of move the x's on the same side, what ends up happening? You don't get anything, right? You get a whole bunch of nothing on both sides, right? So like, here's what I'm suggesting. This would result in 0 equals 0, which is true, just not especially helpful to write down. So what does it mean when you get to a point where you're seeing that the sides are identical, absolutely identical? Well, it actually means that all solutions work, or all values. In this case, we're working with integers. So in particular, integers for us are solutions. Every number works in this equation. So probably written down, you'd say something like that the answer is all integers. Clearly a special case. That's not what typically happens. Typically we get something that happened like on part A, where a specific number would work. Now if at some point you did get the answer all integers, it'd probably be a good idea to try a few and see that they really work, right? And generally speaking, when I try solutions and try to see if things work, I try something for sure that's positive, something for sure that's negative, and maybe 0. And maybe a couple other extra things just to be sure too. But you kind of want to cover the spectrum with your integer sort of signs. Make sure that a positive, make sure that a negative, make sure 0, and go from there. Any questions on this one? All right.